Okay, so this here is gonna be a recording of my current talk. It's titled Open Problems about the Simplex Method. Over the past year, really, I've been lucky enough to be invited to give this talk about 15 times. So it's been a year, and I will be retiring this talk from the offline speaking circuit soon, I guess. And so after this much practice, I feel ready to record it for an online audience. So that's what we're doing here right now. Cut to the video. Hi everyone, thanks for being here. Thanks for having me. So yeah, today's talk, it will be about open problems and about research directions. I will mostly be telling you about questions, and I do not have a lot in the way of answers yet. So with that out of the way, let's remind ourselves just of the basic setup and establish our notation. So we're going to be solving a linear program, which is anything that can be written in the form maximize C transpose times X subject to AX at most B. Here, the matrix A, the right-hand side vector B, and the objective vector C, they're given to us. And it is our task, first of all, to find if there exists a vector X, such that the system of inequalities, AX at most B, is satisfied. Such an X we would call feasible. Note that here that we are comparing two vectors of equal length. So this inequality sign, it means that we are making a coordinate-wise comparison. Now, if there exists a feasible X, then it is our task to find a feasible X for which the inner product, C transpose times X, is as large as possible among all feasible X's. Now, for our last bit of notation, we assume that the vectors C and X, they live in Rd, the dimensions. The vector B lives in Rn, and the matrix then lives in Rn times D. In linear programming terminology, we would say that we have D variables and N inequality constraints. So we will not be doing all that many formulas today. Let's draw a picture instead. So the set of all x's that satisfy ax at most b, it is a convex polyhedron, such as this guy here. The objective vector we can think of as a direction. And now what we want to do is we want to find the point in the set, in the polyhedron, that is the furthest possible in that direction. Linear programming is an important computer task. Like, people pay tens of thousands of euros to get good software for solving these problems. And in my research, I would like to understand why the good software, why it works. And so one of the most important algorithms that we have for linear programming, it's called the simplex method. It's usually described using a lot of complicated linear algebra, but since we are drawing pictures, let's think of it this way. Without loss of generality, turns out we may as well assume that the feasible set is non-empty, that there are points that are feasible. And we can also assume that we know a vertex of this feasible polyhedron. So that's what we start with. And what the simplex method does is that in every round, it will move. It will move across an edge of the polyhedron to another vertex. It will pick an edge, usually such that it will move towards the objective direction, and then it repeats. So it keeps moving from vertex to vertex to vertex until at some point it finds an optimal vertex, one that can't be improved any further. And that vertex, that will be the solution to the linear program. So one of these steps from a vertex to another vertex, it's called a pivot step. And the main question that we will be asking ourselves today is how many pivot steps does the simplex method need before it finds an optimal solution? For those of you who know what degeneracy means, today we will pretend that it doesn't exist. Do not ask me any questions about it because I will not answer them. It's really not important for what we're doing today, for like really our purposes. And so the simplex method, it's the oldest algorithm that we have for linear programming. We have around 77 years of practical experience with it, and the evidence is very clear. Like in practice, the simplex method needs a pivot steps that is linear in the dimensions. So we would say it's linear in n minus d for the most part. And although this is a rule of thumb, it is a very, very robust rule of thumb. As far as I'm aware, there are actually no known practical linear programs that require even 5 times this number of pivot steps. And so naturally, theoretical computer scientists were asking, maybe we could prove that the simplex method, it requires a number of pivot steps that is linear in n and d. Unfortunately, these hopes came to an end quite soon. Because as it turns out, if you were to give me any simplex method, any variant of a simplex method, then I can go into my lab and I can construct a family of evil linear programs. Ones that would trick your simplex method into requiring exponentially many pivot steps before they finish. We say here that the simplex method has exponential worst case complexity. And this brings us into an interesting position. All our observations indicates that the simplex method is always fast, but our proofs suggest that the algorithm, it can be very slow. Good in practice, bad in at least one kind of theory. Naturally, people have written sophisticated papers to try and understand more of what is going on. So people have proposed a number of different models to try and explain the good behavior of the simplex method. Some of these models include slack ratios, average case analysis, lattice polytopes, smooth analysis, and maximum subdeterminants, to name just a few of them. When we find ourselves in this kind of position where we have many different competing theoretical models, we have to keep in mind like one important question. How do we know that any of these theories has any bearing on reality? How can we evaluate which is the right one? Do we have a right one? Just because all of these theories involve like mathematically rigorous proofs, that does not necessarily mean that they're also like scientifically meaningful. In fact, name almost any scientific question and it shouldn't be that hard to come up with mathematically rigorous arguments that give scientifically worthless answers. Now, let's examine one of these theories in more detail. For this talk, I chose to discuss smooth analysis, both because it is the most popular theory that we have, but also it's the one that I personally know the most about. So the definition of smooth complexity goes as follows. We assume that there is some LP that we want to solve, some idealized LP living out in the Platonic realm. It consists of data, A bar, B bar, and C, and they are appropriately normalized for the rest of the definition to make sense. Now, we don't have direct access to the Platonic realm, so we must go out into the world with our rulers, with our thermometers, and we have to measure all the required numbers. Instead of the exact data, this process gets us the data plus some random perturbations added to it. These are our measurement errors, let's say. And so we can assume that our measurement errors, let's say that they are independent and they are Gaussian distributed, each of them having standard deviation equal to sigma. So now what we do is that we consider the expected number of pivot steps required to solve the perturbed linear program. So to do that, we define the smooth complexity of our algorithm to be the maximum over the idealized data, A bar, B bar, and C, of the expectation over the noise, A hat and B hat, of the number of pivot steps required to maximize C transpose X, subject to A bar plus A hat, X at most, B bar plus B hat. With this setup, you can prove that the smooth complexity of the simplex method is bounded by a polynomial in n, d, and 1 over sigma. That is the number of constraints, the number of variables, and 1 over the standard deviation. Note that the 1 over sigma must be in there, because if sigma goes to 0, then we will be adding less and less error, meaning that the left-hand side here in this inequality, it should converge to the worst case complexity, which we know is very large. So to make the inequality still hold true, the right-hand side must also grow very large. And the dependence on 1 over sigma is what accomplishes that. So we have a polynomial upper bound here, and a lot of long and complicated papers have been written to make this polynomial as small as possible. I've written a good fraction of these papers. So now, do we have any way whatsoever of verifying that smooth analysis theory is scientifically meaningful? Could we have some type of experiment in which we could see that the theory makes predictions and that those predictions hold up in the experiment? If you ask this question to any mathematician, they will say, yes, of course you can. The experiment is right there in the definition. You pick your favorite A bar, B bar, and C. Then you go on to sample A hat and B hat as specified in the definition, and then you measure the number of pivot steps required on the resulting linear program. This is what I thought as well, and so naturally we've done that exact experiment. We used a variation of Benthal and Nomorovsky's extended formulation, and then we went and we added Gaussian distributed perturbations to it. And finally, we used a proxy for the number of pivot steps that we have had developed in our theoretical work. And the outcome of this experiment is plotted in this graph. You can see 3 series of data points in different colors. One for 14 dimensions, one for 19 dimensions, and one for 24 dimensions. The horizontal axis shows the standard deviation of the noise that we added, and that results in the instances, and then the vertical axis measures our proxy for the number of pivot steps required to solve the perturbed linear program. Note that this is a log-log plot. Both of the axes use a logarithmic scale. That means that any straight line in the plot, it corresponds to a polynomial fit. I eyeballed what I thought was a nice fit and plotted the resulting black line for the graph of sigma to the minus 3/4. This plot, it is about as beautiful as any plot can be. If sigma is large at the right side of the graph, then the number of pivot steps is small. And as sigma gets smaller and smaller, the number of pivot steps grows larger and larger. At some point, every data series it hits a ceiling, and that ceiling happens exactly at the worst case complexity. So really, this is exactly what we expected to see. And we can even draw the existing theoretical results into this plot. The strongest upper bound, it looks like this, quite a bit above the measured points. Due to the ceiling, we need a separate lower bound for every series of data points, but they look like this. And so now we have our data. What can we learn from this? Well, I will say that we can tell that the theorems are not tight. The data points are not close to the lower bound or the upper bound. meaning that we might be able to improve on both of them, even with our existing lower bound construction. But I would argue that this data can fundamentally not tell us if the theorems are useful. And that is because the real world played no part in any of this. We used a synthetic initial LP, we added synthetic perturbations to it, and then we used a synthetic proxy for the number of pivot steps. We used no real data, no real measurement error, and no real algorithm. So let's be honest, this here, it's not an experiment. It's a calculation. It's closer to the theoretical proofs than we did than it is to testing the real world phenomenon that we had set out to model. So synthetic data might not be the answer for us. So my next thought is that maybe there exist Gaussian distributed linear programs in real life. So I searched through a good amount of the literature, and it seems that the best fit in any type of linear program, it's called a diet problem. In a diet problem, we have a list of 77 different foods, or like any number, but traditionally we have 77 types of food. For every one of these foods, we know how many nutrients there are inside. When this LP was first formulated, only 9 nutrients had been discovered yet, so 9 nutrients are what's in the data. Now, the optimization problem is as follows. If we know how much every ingredient costs, and we know how much of each nutrient a person needs, then we could theoretically compute the cheapest diet that meets all our nutrient needs. We make one variable for every food item. For every variable, we add a constraint to indicate that we can only eat a non-negative amount of that food. Otherwise, it wouldn't make sense. And finally, we add one constraint for every nutrient, stating that the sum total of the amount of nutrient consumed, it should add up to the daily need for that nutrient. So it's a linear program, and people have solved it. In fact, it was the first linear program that was ever solved using the simplex method. And we might assume that this LP is Gaussian distributed. I imagine that at some point someone had, say, a red onion, they threw it into their thiaminometer, and out they got a noisy measurement for the amount of vitamin B1 in a red onion. Repeat that for every food and every nutrient, and you get a table full of measured data with measurement error. So could this be a good fit to test our smooth analysis theory with? Maybe, but first, it would be dishonorable to mention the diet problem and not talk about its background and its context. So let's do that now. Let's talk about the history of this computation and about some of the ways that it has been used. George Stigler was an American economist. He was a key figure in what's called the Chicago School of Economics. Some of his colleagues described him not just as a conservative economist, but as the conservative economist. He was opposed to most forms of government interference in the economy, including rent control, price controls, and most relevant for this video, he was opposed to the minimum wage. So imagine, it's the mid-1940s. The USA has effectively no minimum wage at this moment, and Stigler is determined to keep it that way. So he writes this sweet but short paper where he argues that minimum wage legislation is both bad for total economic productivity and ineffective at providing aid to those who need it most. It's a very theoretical paper where honestly little of the relevant data plays into his discussion, but his conclusion is clear. A minimum wage is not the way to go. He adds some discussion of alternative policies you could use instead, but I think he's clearly not enthusiastic about any of them. I want us to focus on the second to last paragraph, where he reveals, I would say, an important insight into his worldview. One final point. We seek to abolish poverty, in good part because it leads to undernourishment. Now, this is quite the opinion, right? Saying that if somehow we had another way to eradicate undernourishment, then poverty wouldn't be all that bad anymore. Well, after this, he goes on to explain that undernourishment, it actually occurs not just among poor people, but in all income classes. So he concludes that undernourishment, it happens because people don't know how to feed themselves on the budget that they have. And so ideally, the government should install an education program to teach people how to effectively budget their food expenses. So that paper, it was published in 1946. Just 1 year earlier, we can see another paper by his hand, the one where he introduces the diet problem. Stiegler is the one who came up with it. So he observes that academics have previously investigated and recommended different low-cost diets to consumers. But he decides to find out what a true low-cost diet would look like, using measurement data from the young field of nutrition science. And although it's known that not all vitamins, not all minerals might have been discovered yet, he does not let that stop him. And so he goes and he successfully computes a minimum cost basket of foods satisfying all 9 nutrient needs for the year 1939. His diet, to call it, it consists of only 5 ingredients: flour, milk powder, cabbage, spinach, and navy beans. It costs less than $40 for a full year, which he observes is 2 to 3 times cheaper than existing low-cost recommendations. He goes on to write, these low-cost diets of the professional dietitians thus cost about 2 or 3 times as much as a minimum cost diet. Why do these conventional diets cost so much? The answer is evident from their composition. The dietitians take account of the palatability of food, variety of diet, prestige of various foods, and other cultural facets of consumption. Primarily on such grounds can one explain their emphasis on meats and the inclusion of sugar. There's a footnote where he writes, tax-supported bureaucrats and professors may also have another reason for certain of their practices. I don't know what that other reason is that he's accusing his colleagues of, but it does not sound good. So, given how close these 2 papers were published together, it's likely that he was working on both of them at the same time. And I would argue that if we see these 2 papers in the context of each other, then we can recognize that Stiegler, he considers undernourishment to be the main bad consequence of poverty. And he argues that when properly instructed, people could feed themselves on a budget that is 2 to 3 times lower than recommendations and 2 to 3 times lower than what is common among the poorest households of the time. Effectively, this linear program is part of a political argument of his, an argument to lower the poverty line and to make food poverty be more politically acceptable. It's a calculation of minimum resource need as an argument for reducing resource availability. The diet problem is part of most textbooks on linear programming. It's very popular among college professors as an example. So let's look at one of them. Let's look at one book. Right. The kitchen manager for Sing Sing prison is trying to decide what to feed its prisoners. She would like to offer some combination of milk, beans, and oranges. The goal is to minimize cost, subject to meeting the minimum nutritional requirements imposed by law. The cost and nutritional content of each food, along with the minimum nutritional requirements, are shown below. What diet should be fed to each prisoner? Sing Sing prison is a real prison. Take the Metro North Railroad, the Hudson Line up from New York City, and right before Austining, you will ride through the prison. The application of linear programming to prison diet is not fictional either. Already in 1971, the Pennsylvania Bureau of Corrections started doing this. They write, "This is the so-called housewife's problem, where the housewife wants to satisfy the daily needs of proteins, fats, carbohydrates, and so on for the members of her family at a minimum cost by choosing from a list of different types of food available." The Operations Division of the Bureau started this project in 1971 with consultant help from Pennsylvania State University main campus. Their computer package on linear programming was used to plan the menu at each institution for the staff and the residents. The program was then field tested and later closely monitored by Pennsylvania State University for its success. The plan is now fully operational with high success. The New York City Department of Corrections has recently started a similar program on food service planning and inventory control. So we know that linear programming based diets were fully operational by 1975. In 1984, we can read about university students in criminal justice administration who are learning about linear programming and about the simplex method, with food cost minimization being the main class of example problems in a material. Also, in the 1970s, the United States started its campaign of mass incarceration, and they see a major shift towards retributive justice. Alongside linear programming comes a move to centralize food procurement and meal planning in order to control costs. Food quality has been observed to decline steadily as the process became more and more centralized. And even over the past 3 decades, we've seen a further and further decline in prisons' food spending per person. Today, the majority of US states spend less than $3 per person per day to feed incarcerated people. Mealtime, it's described as daily degradation. Fresh fruits and vegetables are rare. Meals consist more and more of ultra-processed food. As many as 94% of surveyed incarcerated people do not receive enough food to feel full. Portion sizes have decreased in size so much that people are even engaging in gang activity or in sex in order to get access to food. This poor food situation inside makes people feel angry or depressed, and the unhealthy eating habits they develop inside go on to have continued impact on people's lives after they get out and back into their communities. Now, of course, we cannot directly attribute all of these issues to the diet linear program. But it is clear that these calculations and these management principles have affected real people's lives. And at least on a technical level, linear programming methodology is very capable of causing many of these exact issues. What exactly the effects of linear programming were, and whether similar optimization methods are still used for US prison meal planning today, that will have to be a subject of further research. I have one more example. This is the one that's been causing me sleepless nights. In 2007, Hamas took over the government of the Gaza Strip. What follows was a 3-year-long blockade on both people and goods, which lasted in that severity until the aftermath of the 2010 Freedom Flotilla. During this time, 2007 to 2010, the amount of important goods in the Gaza Strip had decreased by 80%, causing a steep increase in poverty. Though most people manage to get the calories they need, less than a quarter can reliably access a healthy and balanced diet anymore. I will now show you a slide deck that Israel's Ministry of Defense presented in courts. I'll be using an unofficial English translation, courtesy of the Israeli human rights organization Kisha. The deck is titled Food Consumption in the Gaza Strip, Red Lines, and it is dated January 1st, 2008. It opens by stating that Israel will limit the entry of goods into the Gaza Strip, approving only 106 trucks per working day to enter carrying basic humanitarian products. The analysis performed in this document is done with the goal of preventing malnutrition. Now, preventing malnutrition is important to Israel. If nothing else, international humanitarian law is very clear that starving civilians is not allowed. And so that by itself makes it important to have work showing that you are intending to follow the law. The first slide ends with a mention that the Ministry of Health is working to calculate the minimal subsistence basket. This minimum basket allows for nutrition that is sufficient for subsistence without the development of malnutrition. In a later version of the same document, we can read, in order to allow for a basic fabric of life in the Gaza Strip, the Deputy Defense Minister approved allowing 106 trucks carrying basic humanitarian products into the Gaza Strip, including 77 basic food products. A few slides later, we find a preliminary calculation of food allowances for a range of gender and age categories. There is this table listing exactly how much grain, vegetables, fruits, milk, meats, oil, and sugar might be required. Although these numbers are said to be somehow based on Israeli standards and not on minimum subsistence thresholds, the data in this table shows clear signs of algorithms having been used. Most of the figures in this table have 4 digits of accuracy, which is way more accurate than any measured data about nutrition of food will ever be. We can also see multiple cells listing the number 0, such as the one describing how much oil all girls between ages of 11 and 24 might need. Finding numbers at their lower bounds, like 0, that's a telltale sign of linear programming or other optimization algorithms. There are more detailed slides taking into account the Gaza Strip's internal food production and what goes on the Carney conveyor belts. I won't bore you with those, but I do want to point out slide 13, which lists exactly what nutrients are added to fortified wheat in what quantities. Clearly, exact nutrient content played a part in their calculations. On the final slide, we read that their model, it says that 104 trucks of food are required for the Palestinians in Gaza. 104 trucks of food on a total number of 106 trucks, which must somehow leave room for everything else in life. Hygiene products, medical equipment, clothing, books. The Ministry of Health will proceed to formulate a more minimalist model, which they expect will be 20% lower than the one used in this analysis. The later version of this document, which uses the minimal subsistence model, it will find a basket of foods that fit the restrictions with less than a fifth of a truck to spare. A very close coincidence to have worked out that way if it was a coincidence. Let's take a moment to recognize what happened here. Israel imposed a restriction of 106 trucks daily to enter into the Strip. Months later, they did an analysis and found that 106 trucks daily would be insufficient to allow the basic fabric of life in Gaza to continue. But instead of loosening the restrictions, they go on to pursue an even more minimalist analysis, one that ends up making the pre-existing restrictions seem permissible by only the smallest of margins. What's not clear at this point is whether the size of this margin is due to a true coincidence, due to Israel somehow having cooked the books for this analysis until the number worked out, or whatever they did for this analysis, a similar or identical one was used to set the limit of 106 trucks in the first place. This is not clear. Once again, we have no smoking gun evidence that linear programming was used to determine or to justify this embargo on food. The few documents that we do have, they were the result of stellar investigative journalism in the newspaper Haaretz, and a subsequent years-long legal battle by Gisha. We might never have solid evidence proving one way or the other that linear programming was used in order to enact the harshest possible food restrictions that could still be argued not to violate international human law. But linear programming would be the perfect tool for that. The International Covenant on Economic, Social, and Cultural Rights is a treaty that was signed in 1966 and came into force on January 3rd, 1976. It describes many of our basic human rights, like the right to health, to education, work, trade unions. Most important for our current talk today are the rights to an adequate standard of living, including adequate food, and the fundamental right to be free from hunger. Note that these rights, these universal human rights, they apply to everyone, including people who are incarcerated, or people who are poor, or people who live under occupation. The right to adequate food is worked out in detail by the appropriate committee in a document called General Comment Number 12. They explain that this right to food, it covers a lot of ground, including accessibility, availability, and acceptability of food. Because people care about food for many reasons beyond just nutrition. And what the committee writes is that these values need to be taken into account when it comes to the right to food. In fact, they explicitly write, the right to adequate food shall therefore not be interpreted in a narrow or restrictive sense, which equates it with a minimum package of calories, proteins, and other specific nutrients. Well, this is awkward for us optimizers, because our linear program, the diet problem, was doing exactly that. It said that a diet is feasible, it's permissible, whenever it satisfies these minimum constraints for calories, proteins, and other specific nutrients. I could not imagine a more explicit condemnation of the diet problem than exactly what the committee writes here. Note that so far I've only been talking about the right to adequate food, but perhaps just as relevant is the fundamental right to be free from hunger. we have to analyze technology not only in a case where everything goes according to plan, but also under real-world circumstances. And the diet problem, it explicitly models nutritional adequacy, which we might say has to do with freedom from hunger. But what if we made a mistake somewhere? How can we be sure that our data is correct? Because any error or inconsistency, it could be exploited by the linear program to get a better solution. And there will be inconsistencies, since measuring the nutrients in food, it's a process that is complicated, inexact, and where even there is some amount of freedom of choice for the measurer. As far as I'm aware, nobody really runs studies to fully independently verify that some linear programming computed diet actually satisfies all a person's nutritional needs, let alone that it would account for the differences between different people's nutritional needs or for the non-nutritional requirements that food has. When you are in a position to limit people's consumption to a certain portion size, such as in the examples I just mentioned, then you have to make sure that the portions are sufficient for everyone, because the right to be free from hunger, it protects everyone. Not 50% of all people, not 99% of all people, everyone. And as far as I'm aware, just the technical and scientific know-how to do that kind of verification, I don't think it exists at this moment. Now, I'm not saying that if you use or you teach the diet linear program that the UN will come bust down your door to arrest you. But what I am saying is that you might be placing yourself or your students in a position that is both legally and morally questionable, especially when you seek to determine what foods a person or people should have economic or physical access to. It really doesn't matter here whether you're telling yourself that you're seeking to lower food access, or you're seeking to certify that a certain level of restriction is not too much. Because in linear programming, the greatest lower bound is also the least upper bound. Okay, so let's get back to what we were doing. We have this linear program, and back in 1948, they used it to benchmark the simplex method for the first time. To solve the diet problem, they performed 15,000 multiplications, a similar number of additions, and slightly over 1,000 divisions. Could the theory of smooth analysis have predicted that this calculation would be fast? I think probably not, if we're honest. The specific simplex method variant that we can analyze, it's simply too different from what they would have used in their benchmark. Also, the diet problem has all of these non-negativity constraints, which are not being perturbed, and the theory can't handle that. And more generally, the measurement error that is in the data is just not distributed in the way that we theoretically need it to. So if there is anything that we can learn about our theorems by looking at these types of linear programs, I don't know what it is. I do know that if we wanted to learn something, that would require a lot more deep thinking to figure out what and how. Now we get into the controversial part of this talk. I'm going to argue that smooth analysis has even more fundamental issues. Ones that suggest that even the most qualitative of conclusions are actually unfounded. So if you looked at linear program at smooth analysis, you took a million steps back, and you intended to summarize the takeaway message of smooth analysis theory, then probably what you would say is the lesson here is that more noise is more better. You expect that if you add more noise to your input data, then you will get further away from the worst case complexity, which means that your algorithm will work more effectively. Now, practitioners, people who write software for linear programming, I'm going to argue, it's controversial, but I'm going to argue that they say the opposite. To see this, we must observe a typical bit of advice that they give.
All floating point numbers are rational in 64 bits or any other finite bit precision. So we are going to give up some accuracy, but again, we do want to go with 16 decimal places. So make sure to use all 16 base digits.
So that was Ed Klotz, one of the most knowledgeable people in the world when it comes to linear programming. And if you will permit me to interpret his words, I would say that what he is saying is that you want to express your LP data as exactly as possible. Roughly, if you have more precision, if you have less noise, then that is more good. Which is the opposite takeaway from smooth analysis, where we said that more noise is more good. Now, not every practitioner or theoretician agrees that their advice contradicts smooth analysis theory. But enough people agree with me that I think we can have reasonable doubts about more noise is more good being even true on like a moral level. Finally, let's open one last can of worms. So I told you a lie already on the first slide. This geometry that I drew for you, it doesn't exist. The geometric picture would have you believe that the set of feasible solutions is fixed, that it wouldn't change during the simplex method's running time. And that belief is simply not true. It's not true because of a number of implementation techniques that exist in all serious simplex method computer codes. So these codes, they have to deal with the realities of numerical linear algebra. They only have finite precision to work with. And as part of that reality, they have this technique, it's called bound shifting. And basically, think of bound shifting as a way of recovering from any mistakes that you might have made due to the floating point imprecision. At some point, these techniques, they started to get more and more mature, and people learned that you can also use them to mess up intentionally and speed up your algorithm. And you can always recover from them with the techniques that we developed. And so that leads to these other implementation techniques called bound perturbations and Harris's ratio test. And if you talk to any practitioner, they will tell you, you have to implement this. Like, if you don't do this, then your code will not be good. So what this means in the end is that a lot of the concepts that we have in linear programming, they don't respect even the most basic theoretical assertions that we make about them in textbooks. Everything you learn in undergrad is false if you look closely enough. Can any of our existing theory be recovered? Can it be fixed to work with the real world scenarios? Can we use the real world implementation techniques to prove stronger theoretical results? We don't know yet. And so I think it will be a huge topic of research over the coming decades to see which of our basic theoretical results and constructions make sense in the world of floating point arithmetic, and which of the methods used due to floating point arithmetic could maybe even speed up our algorithm. Okay, let's wrap up. So what we've learned today about the simplex method is that basically all of our existing theories are untested. It's unclear what testing them would even mean. And moreover, all the theoretical work we have is about a vastly oversimplified presentation of the algorithm. In short, we've seen that there's a lot of directions for future work. Thank you. That was it for the talk. Thanks so much to everyone who invited me to speak on this topic. Thanks to all my in-person audiences for your insightful comments and questions. And thanks to you for watching this video till the end. now there's time for questions. So if you have any questions, comments, feel free to drop them down below in the YouTube, and I will do my best to write a response to each of them. Thanks.